Okay, well, we will start the session leveraging Spark for cluster computing. Please welcome Mr. Robin.
Hi, everybody. So thank you very much for being so many. My name is Robin. I work at RIT in Rakuten Institute of Technology in Tokyo as a data scientist. And so today I'm going to talk to you about Spark, which is a framework for cluster computing. It's a platform. So I'm mainly going to explain to you why we use Spark, but I'm not allowed to disclose any information about specific projects, so not so much about the how. So my apologies for that. Okay, so what is Spark? So if I had to put it shortly, it's the future of open source map reduce. What a bold statement. So why so? So why did we decide to start using Spark here in Rakuten? So if you are familiar with the Hadoop stack, it's quite heterogeneous. So you start with the Hadoop framework, which is quite low level, so only dealing with map reduce and combines and shuffles and very low operations. And then on top of that, you start adding frameworks such as Hive and Mahout, for example, or Pig. So all of those frameworks, I'm not making any criticism here, all this software is very good, but they kind of started Spark because they wanted a fully integrated analytics suite and cluster computing framework. So it's kind of next iteration of that kind of stack. And it was started by Berkeley AMP Lab, and now it's transitioned to the Apache Software Foundation. So we want something more homogeneous. So on the surface, Spark is very similar to Hadoop. So it's a regular distributed computing platform with a driver program, some cluster manager, worker nodes, and so forth. So it looks like your regular horizontal scaling kind of thing. It relies on HDFS, so more than Hadoop, it's basically relying on HDFS. You can run it on Yarn Mesos, or also in standalone mode. And so the goal is to do basically MapReduce operation and general cluster computing. However, there are some key differences with the usual stack, mainly Hadoop. The first one is the RDD, so the Resilient Distributed Data Set. So everything in Spark revolves around that idea of the Resilient Distributed Data Set, which is so more higher level than what you're used to work if you ever work with a Hadoop framework, where you are making your operations in MapReduce and so forth. You can think of the RDD as our data frame. So in R, it's the same thing. Like everything is around the data frame. Or Python, if you use pandas, everything is also data frame. RDD is more abstract than the data frame. So data frame has specific types. It's not the case for the RDD, but the idea is the same. And so everything revolves around that Spark. So when you do several operations in a chain, everything is just transformation from one RDD to another, and so forth. With some end operation, for example, saving as a HDFS or things like that. Okay, so this is what Spark code looks like usually. So it's reminiscent of the higher languages that we have built on top of Hadoop. And so you have a file, so for example, a log file with a line, maybe a log or something. So this is for text, so counting words. And then you just do transformations one after another, and every output is an RDD. And so in this case, at the end, you save as a text file, right? So this is a regular count word example. You can say this pretty short and easy to write. It has better resource utilization than the regular stack. So let me explain. Spark allows you to cache everything in memory, which is, well, of course, it makes things much faster than doing I/O on the disk all the time. So you can have several levels of persistence, actually. So you can cache to memory, you can decide to cache and swap if you don't have enough, and so forth. So in the example on the right, what you would do, for example, you read blocks from the disk. So for example, log files or whatever. You compute your aggregates, you store that in memory, and then you do other transformations. And that will make things much faster in practice. Also, so this sort of started with Hadoop 2, but it has better resource utilization. So of course, if you hack your own Hadoop framework and tell it to use several cores and so forth, it's going to work, but this comes right off the shelf with Spark. So what this means is that on each node, if you have several cores and you Spark several executors, so those are like subnodes, but on the local machine, each core is going to take each local block. And so that's sort of how it works. And one thing, so it becomes hybrid between vertical scaling and horizontal scaling, since when you want to use Spark, actually you would want less machines with more cores than the opposite. And you want to take advantage of resource locality. What does that mean? If you have an HDFS, you want your Spark to be on top of that HDFS on the same cluster, right? So when you launch a job, such as the count were before, you spawn, for example, if you're using the Python API, you spawn one Python process per core, and then each of them is going to take a different block. Right. So the resources in Spark are better utilized. So that's one more reason to take it. And they have this nice graph which run on, I don't know which experiment, but it's pretty fast. The third advantage, and one of the most important, I would say, before performance issues, is that it's very, very easy to develop and operate with Spark. So they have the basic Spark is coded in Scala, which gives you automatically an API in Java, and you also have an API in Python, right? So, well, you can see from this code that you can code logistic regression in 8 lines, which is pretty compact. So of course this one doesn't have any convergence criterion or stuff like that. It's pretty simplistic, but still. And yeah, so if you want to bear with me, you would read from a text file. So for example, log, map your point with some function that is defined within your environment to which you talk to Spark. So every time you define a function or something, it's shipped to the nodes directly. Cache that in memory, and then so for the number of iterations that you want, so you define your hyperplane. For the number of iterations that you want, you just define the gradient as a mapping of all the points with partial update. Then you reduce, and then back on the main node where you started this operation, you just minus that to the hyperplane, and then at the end of the operation you have your model. You also get easier analytics because they have interactive shells in Scala and Python, so you can talk to your cluster directly in a very easy manner. And with the Spark context class, you can easily connect from whatever you like. For example, I like to use it from IPython notebook, which makes it very I'll say practical and easy to test and develop iteratively on the go, or do quick analytics without having to launch a bash script or something, or kick a job. So you can have immediate feedback with that. And then the fourth advantage is kind of what I mentioned at the beginning, is that everything is integrated, right? So whereas before you had to set up your Hadoop cluster, then try to run Mahout on that and Hive and so forth. Here you just download Spark and everything is inside the package with higher abstraction. And all libraries that are mimics of the ones on the right, right? So It's easier. You have DBMS-like functionalities, training, machine learning. So for example, when I say easier, you have many useful distributed operators on the RDDs, so the resilient distributed data set, the Spark data frame-ish thing. So most of those operators, they're very useful. So for example, reduce by key or things like that. One I like pretty much is the histogram operator. So you can just ask them to bin values depending on keys. Or a pipe operator. So this is useful if you have to invoke some process on your nodes. So for example, if you're trying to parse Japanese text on many nodes, and you have some morphemizer like a makeup or something, you can call it from there directly. Yeah, so analytics. So you can do SQL-like analytics directly with Spark, which is pretty nice. So it's compatible with the Hive language, so you can transfer what you already have written. You have what they call unified data access, so many file formats that you can process easily, such as, for example, if you have JSON and so forth, you can just run queries on that. One thing that I find really neat is the standard connectivity. So what it means is that you have your Spark cluster with your master, and it's going to spawn ODBC server, and that allows your analytics software, so for example, RapidMiner or R or whatever, to connect to that as if it was regular ODBC interface. They also offer streaming facilities, so storm-ish facilities. So what does that mean? You listen on a stream such as Kafka or ZeroMQ or the Twitter streaming API. And then Spark Streaming is going to separate that in several batches, so very storm-ish approach. And then using whatever you have coded in Spark, you can process that data and then save it to HDFS or database, your analytics database or whatever. So of course, one of the main applications of distributed cluster computing is machine learning. And so they have the machine learning library, which allows you to compute some statistics. So for example, hypothesis testing with chi-square, so classification and regression, logistic regression with HGD or LFBGS or something. Collaborative filtering, so for recommendation, item. Clustering with k-means, dimensionality reduction. Feature extraction, so you can do TF-IDF extraction. Also, you can do word-to-vec, which is pretty neat. So it's they have a bit less functionality than Mahout, I think. There are rumors about Mahout being merged in machine learning library, but you will have to check on that. Although many Mahout contributors are working on Spark. DML data. Then another neat thing is the graph processing capability. So they have this GraphX thing that is integrated. And so using that, you can compute PageRank, connected components, and so forth. And it's allegedly faster than JRaph and GraphLab. So you might want to know how much does it scale. So there are reports of deployed clusters of more than 1,000 nodes, which is pretty nice. And they have a huge contribution. So we have open source, and we have open source with many contributions. So we have, for example, our OpenSSL, which wasn't supported enough. And but Spark is like on the total opposite of that. So for example, for the 1.1.0, they had more than 170 contributors, which is pretty huge. So yes. So in conclusion, as I said in the beginning, it's kind of the next iteration of this whole MapReduce cluster computing paradigm. As it's a very unified framework that's easy to program and operate. Very nice resource usage, and so forth. So that's it. So if you have any questions. Yep.
It's a very interesting talk. For Spark and Storm, in which case should we use one versus the other, or do you feel because Spark can do some Stormish stuff with the streaming, we don't really need Storm? Or, you know, is Spark a good general solution that'll handle a lot of transactions, or that type of thing?
So I'll be honest, I haven't used it. So I only know what I read from the documentation, so I don't know specific that much. But I think Storm is more flexible in the sense of how the bolts work and the cluster organizes itself, kind of thing. I think this is basically just reading from streaming data and having thresholds of how you batch your things, and then take that to the rest of the cluster. But don't take my word for it. So
Storm could maybe still be an option.
Yes. And Storm is also very easy to develop with if you use a Trident. I don't know which one works best or any specific cases. The nice thing is that it's already inside Spark when you download the package off the shelf, which is very nice. Anything else? Yep.
So you said that the Spark is in-memory processing. What
Yep.
happens when data is over larger than the memory capacity?
Yes, so wait a sec. Okay, so actually let's look at this. Okay, so here, at the end of the transformations, I'm caching my points with that cache function. One thing I should mention also is that this mapping and everything only happens when it's necessary, so it's done just in time. So that means that when if I execute this line in my IPython notebook directly, it's not going to perform the operation right away. It's going to perform the operation when it's needed. So for example, in that case, or when I say save to text file or whatever. So yeah, back to your question. So that cache operator is actually override of a method that is called persist. And so in persist, you can specify what level of persistence you want for your cluster, right? So you can say memory or memory and swap. You can say put that on disk. So there are many options. I think by default, so if you go over the memory that you have, it's going to swap. It's going to start swapping, right? So that's when you have to make choices of what you want to cache in memory, right? So for example, if you have your logs that are probably very huge, like on the terabyte order, right? You don't want to put that in memory. You want to process it, doing some aggregates, for example. That's going to be smaller, maybe on the order of 100 gigs or something. Then you put that in memory if it's available on your cluster. Right? So yeah, you have to think a little when you do that caching.
When out of memory, how is performance compared with the Hadoop?
If it's starting to swap, I think it's going to get a lot slower.
Close to Hadoop or close to Hadoop? Performance gets close to Hadoop or still faster than Hadoop or when?
I haven't had that case, but yeah, probably gets closer to Hadoop. Yeah.
Thanks.
Sorry. Yeah. Like when you use that memory, you have to know the order of magnitude of the memory you're putting. So yeah, if you start swapping, probably it's going to get slower, closer to Hadoop. Yeah.
Thank you.
Yeah. Yes.
About graph processing. Programming is easier than Jack.
I haven't compared. Sorry. I didn't try Giraffe, so I can answer your question. I don't think it can be more complicated. This is obviously very compact code. So I would say, well, my prior opinion is that it would be at least as easy to program.
Running out of time.
Oh, okay, sorry. So,
Okay.
okay,
Thank you.
thank you very much.